And Coulombs' law describes the magnitude of forces between two charges, and obviously there can be more than two charges acting, but basically it's 2 point charges separated by a distance r, and they're both gonna exert a force on each other. So Q1, which is the negative charge over here, and Q2, the positive charge. So Q1 will exert a force this way onto Q2, so that would be the force of 1 on 2, and then obviously Q2 is also going to exert a counter force, so this would be the force of 2 on 1. They're going to be separated by a distance of r, that's the distance between both of the charges, and r is usually in units of meters, so that everything cancels out later, and r is the distance, obviously, as I said before, and force will be in newtons, charges will be in coulombs, just to get that straight from the beginning. So basically the equation for Coulombs' law basically states that force is going to be equal to 1 over 4 pi E naught times the product of your charges over r squared. So back to our problem. So we have that the negative charge is negative 4 microcoulombs, and then the plus charge is 2 microcoulombs, and then the charge that they're going to be acting on is 7 microcoulombs. And then it's an equilateral triangle, so it's also 0.5 meters away. And I just like to keep things straight, so let's call this Q1 and this Q2, and call this Q3. So we're going to try to find the force that Q1 acts on Q3 and the force that Q2 acts on Q3. So we can draw like just a little diagram over here for what we think what do you call it? The force diagram would look like, the free body diagram. So you're going to have your charge here that is Q3. So you have your positive charge over here that's going to send your vector this way, and your negative charge here that will send your vector this way. So as we can see, we're going to only be operating in the y for this problem. There's no x components. So let's just erase this for now. And we apply that to our force that the equation we talked about earlier. So force is going to be equal to 9 times 10 to the 9th newtons meters squared over Coulomb squared times your charges. And you have to remember to convert your charges. So let's do Q1 on Q2. So that's the force of 1 on 3. So it's going to be 2 times 10 to the negative 6 coulombs times 7 times 10 to the negative 6 coulombs, over your distance of 0.5 squared, so that's 0.5 meters squared. Your units, some units will cancel, meters cancels, coulombs squareds cancel, so you get that the force of 1 on 3 is going to be equal to 0.504 newtons. Okay, and to put that in notation, so it's going to be going up, since you have your positive charges. The diagram I earlier should have erased it. So it's going to be going up, and this is F1 on 3, so that's positive. And then you do the same thing with 2 on 3. So 2 on 3, 9 times 10 to the 9th. And then your charges, you have your negative 4, which the negative goes away because of the absolute value, times 10 to the negative 6 coulombs, times 7 times 10 to the negative 6, over the same distance of 0.5. Since you have the equilateral triangle, square it, and that will be equal to 1.008 newtons. And then to find your resultant vector, you add these two up, but this, you'll notice that since you have a negative charge here, it's going to be going downwards. So it's negative 4 down, and you would rewrite this as a negative 1.008 newtons J, and this as a 0.504 newtons J, and this one's positive. You sum those up to find your resultant vector, and you get that negative 1.008 newtons J plus the positive 0.504 J is going to be equal to negative 0.504 J. So then your resultant vector is going to be pointing downwards, and it's going to be somewhere down towards this side. So this is your negative 0.504 J.